Okay, so this is a continuation of the enthalpy problem. Um, the internet was disconnected in the first video. Apologies about that. So back again to this problem here. So if you are presented with data, and this time basically you are presented with enthalpy change of formation data, and you are asked to find out the enthalpy change of this chemical reaction. So what are you supposed to do? Now, first thing, look at your reaction, see what is made of. So your reaction is made of oxygen, is made of hydrogen, and made of carbon. So the elements here, when you write them down here, they must be in their standard state. The standard state means that the state that you would expect the elements to be in nature. So oxygen is expected to be in the oxygen form, O2, and hydrogen is expected to be in the H2, and carbon is expected to be in the solid state, and these are two gases. So let's write them down here. So O2 and H2, and here we have C. Okay, now this first one, the carbon, the ethane, is made from carbon and hydrogen. So we will draw an arrow here, and the amount of energy that's required to make this is minus 83.6. And then basically also from these elements, we will form the the O2, and we will see what's the value. The value is not mentioned here. Think about it. And from the C and O2, we will form the CO2. So this is in the product side. And here it is minus 393. That is times 2 because you are forming 2 moles of this. And finally, you're forming water when the O2 and the hydrogen mix together. And here you're forming 3 moles of water. So that is 3 times minus 285.5. Okay. So before we continue, we can balance this equation here at the bottom, or these elements. And when you do balance them with one side of the equation. So choose this side with this side and balance them. But before that, let's see what is the value here, if you thought about it. The value here, basically, you're forming oxygen and the gaseous state from oxygen. So basically, it is 0, because basically this oxygen is present in its standard state, and the enthalpy change in this case is 0. So it has a value, but the value is 0. Fine. Let's balance the equation here. So here you have 2 carbons. Here you have 3 hydrogens. And here you have, I'll write it here, 3.5 of the oxygens. If you want to try this with this side, to just double check your answer. So here you have 2 carbons. Here you have how many hydrogens? You have 6 hydrogens. And here you have also 3 oxygens, and here 7. Here you have 4 oxygens, and here 3, so that is 7. And this is 3.5. So basically 3.5 can be also written as 7/2 times O2. So this is 7 oxygens. Okay, so the equation is balanced. So how can we proceed to solve this problem mathematically? Now, mathematically, this is how you do it. Here you have your main equation that you are doing the calculation for, and you'll follow this direction, this and this. Fine. So this is, let's say it's delta H1, this is delta H2, and this is delta H3. Fine. So delta H1 equals to delta H2 plus delta H3, and keep the direction of the arrows like this when you want to do the calculations, and apply them into your problem. Okay, so how can we do this? Let's see. Now, delta H1, which is this equation, here. It's tricky. Which is this equation, fine, equals to delta H2, and this is basically the side of reactants. So basically, here you have minus 3.6. Now, notice that this side here, this arrow, goes against this arrow. So this is your standard sort of format of solving the problem. And you need to see if the arrows in your problem follow the same format or not. If they follow the same format or the same direction of the arrow, then you will keep the sign of the arrow. You'll keep the sign of the enthalpy change. If they don't follow the same format, then you need to change the enthalpy change sign. So in this case here, it will be 3.6 plus 0 for the oxygen. You don't need to write it. And then plus the delta H3, and basically this is for the product side. So here you are talking about the side of the equation. And as you can see, both of these arrows, they are the same direction as delta H3. So here you have minus 393 times 2. If you want to put it in big bracket, plus another one, which is 3 times minus 285.5, close bracket. So here we got 83.6 plus 393 times 2, that is minus 786 plus, that's 3 times 285.5. That's basically minus 6.5, and that is 83.6 minus 786 minus 856.5. So the total answer would be 83.6 minus 786 minus 856.5 equals 2. That is minus 1,559 kilojoules per mole. Okay. Let's see another problem. In this problem here, you are presented with a different set of data. And as you can see, it says here delta H of combustion. So in the case of combustion, you're basically reacting the reactant and products with oxygen. So here it will be with O2, here with O2, and here on the product side with O2. Now, in this case, in the alkene side, here you will have CO2 and H2O. When you react oxygen with hydrogen, you get H2O. When you react the alkane with oxygen, you get CO2 and H2O. So you don't need to rewrite it again. Okay, now let's put the values. So according to the definition, it's the combustion of 1 mole of your reactant or product completely to produce the combustion products. So here for the alkene, it is minus 2717 For the hydrogen, it is minus 286. And for the alkane, it is minus 2877. Okay, now let's balance the equation in relation to oxygen. In relation to oxygen, let's use this side of the equation to balance it, since it's less complicated, and I'll explain why later on. So here you have how many carbons? 1, 2, 3, 4. So basically you need to put 4 here. And how many hydrogens? 1, 2, you have 10 hydrogens, and here 2, so you need to put 5 in here. And in relation to the oxygen, here you have 4 times 2, that is 8, and 5, that's 13. So that is 13 over 2 here. 13 over 2, or 6.5 if you like. Okay, so we can also do the calculation about the oxygen balance here, and this should be this and this. The total of them, it should be 13 over 2 or 6.5 as well. But I'll do this after I finish solving this problem. Okay, now we want to solve the problem mathematically. So again, we will do this. We will say that we have this reaction that we are trying to find out the enthalpy change of it, and we have direction of the arrow going down and direction of the arrow going up. So this delta H equals to this and this. If the arrows here are following the same direction as my arrow, I will keep their sign. If not, I will change the sign, but I'll not change the sign on the cycle, on Hess's cycle. I will change the sign in the calculations when I do them. So let's do the calculation here. So this equals to, look at this here. Now, in this one is following the same direction as this arrow, the purple arrow. So that is, I will keep it sign. So it's minus 717. And then plus minus, that is minus. Here, I'll just write it for clarification. So plus minus the other one, the O2, that is minus 286, 286. And then the other arrow is going against the purple arrow. So that means I need to change the sign. So plus, and the sign here is negative, so I'll change it to positive. So plus 2877. I'm here trying to cater for everyone. So I know that lots of you understand these basic processes, but you need to be patient. So here it is 2717. This is minus 286. And here you have 2877. So therefore, basically, the total is 2877 minus 286 minus 2717. So the answer is 126 and minus kilojoules per mole. Fine. So that's it. Now I chose to balance the oxygen with this side because it's easier. Fine, where I'm pointing, it's easier. But also, let's prove that this side here, it will also result in the same amount of oxygen. Now let's see. In this side here, you have two equations if you want to analyze them. Firstly, you have hydrogen reacting with oxygen, giving water. So basically here you have, if you balance the equation, here you'll have one water molecule. And then we have the other equation, that is the alkene. So that is CH3, CH2, CH, CH2, and O2. That will give us CO2 and water. So if we count the number of carbons, we have 4 carbons, so add 4 here. If you count the number of hydrogens, so that is 1, 2, 3, 4, 5, 7, 8, 9, 7, 8. Oops. 1, 2, 3, 5, and 8. So this is 4. And therefore, basically, you have here you have 4 times 2, that is 8. And here you have 4 times 4, that is 4. So 4 and 8 is 12. And here we have O2. So here you will add 6 in order to balance the chemical equation. So 6 times 2 is 12, and here you have 12 as well. So 6, here you have 6, and here you have half. So that is basically 6.5, or as we said earlier here, that is also 13/2, which is 6.5. Okay, and this shows that they're both sort of equal. I hope that was beneficial and sort of made sense to you. So these are basically, to summarize, are the 3 types of problems that are frequently asked in the exams. It's either the bond enthalpy, when you are given bond enthalpies and you are asked to predict the enthalpy change of chemical reaction, or if you are given data, and this data can be the data of combustion or data of formation of the chemical reaction. In this case, you need to pay attention to the arrow, where the arrow will be pointing in the Hess cycle. In case of formation, it will be pointing upward because you are forming the reactant and product from their elements. In case of combustion, the arrow will be pointing downward because you are reacting the products and the reactants with oxygen to form the combustion products. When you do the calculation, follow this pattern here, where I'm pointing. Yeah. So basically, the enthalpy change of chemical reaction that you are trying to solve is equivalent to this plus this. So look at your arrow, see if they are in the same direction as this pattern or against it. If they are in the same pattern, then you can keep the sign. You should keep the sign. And if they are against it, you will change the sign of the enthalpy change. But when you change the sign, just change it in the calculation, but not on the cycle itself. I hope that was beneficial to you. And talk soon. Thank you very much.